Yeah, hi friends. In this video, we would like to discuss about nodal analysis. Nodal analysis. Okay. So it can be applied for planar as well as non-planar network. So I can write it is applicable for planar and non-planar networks. So I can go with the procedure. What is the step-by-step procedure we will discuss to find what are the node voltages. Okay, first point, as we discussed in last video, that is mesh analysis. So I can go with the same procedure here. First of all, you can identify total number of nodes, total number of nodes in the given network, in the given network. Second point, assign the voltage at each node. Assign the voltage at each node. One of the node can be taken as one of the node can be taken as reference node, reference node, and and its potential should be equals to ground potential. Ground potential, you can take it as a 0. Next, third point, you can develop KCL equations KCL equations at each non-reference node, at each non-reference node. And last point, by solving KCL equation, by solving KCL equations, find node voltages. Okay, this is the procedure to find the node voltages. Okay, let's see a simple problem here. Take an example. Find node voltages. Find node voltages. Okay, in the given circuit. In the circuit shown below. Okay, so take the circuit here. Resistor connected in series with a source. Again I have a resistor. Again I have a resistor, and there is a current source I am connecting. Now the values of this, you can write 4 volts. This is 1 volt. You can take this is 1 volt. Yeah, you can take one more source voltage here. You can take that is 2 volts, plus minus. This is 2 amps current source, and here that is 10 volt. Now, as per the procedure, the first point, we need to identify how many number of nodes are there. There are 2 nodes. This is one node. This is a common node, and here also it is a common node. You can take this is a second node, and this node voltage or potential of this node is equals to the ground, or I can take it as a reference node. Okay, reference node, and this voltage should be 0. Okay, solution for this. So second point, assign the voltages at each node. So I can take this is V1 and you can take this is V2, which is equals to 0. Okay, and I can apply the KCL equation. I can develop the KCL equation here. So this at node 1, apply KCL at node 1. So while applying KCL at node 1, that is V1 is the highest potential point and all the currents are moving away from that point. You remember that one. So take this is I1, take this is I2, take this is I3. I1, I2, I3 currents are moving away from the node 1. Why? Because V1 I am taking it as a node voltage and it is a highest potential point I am considering. So the current are always moving away from that node. So I can write as per KCL statement, sum of the currents at that node is equals to 0. I1 plus I2 plus I3 equals to 0. Then I1 you can write the current flowing from V1 to the ground. So I can write this as V1 minus, this is the highest potential point, all the voltage present in that branch should be removed. Removed means you can take subtracted from the highest potential point. So V1 minus 4 volts, this is already plus terminal, so you can take minus 4 and minus V2, that value is 0 by that branch resistor 1 ohm, plus I2, that is a current flowing, that you can take V1 minus V2. Yeah, there is a voltage source, that is minus 2 minus 0, that is V2 by that branch resistor 1, plus I3. Look at the I3, current will flowing in this path, but original current direction is given, that is opposite. So you can directly take the current direction or current value minus 2 equals to 0. So now you can write V1 minus 4 plus V1 minus 2 minus 2 equals to 0. So 2V1 minus 4 minus 2 minus 6 and minus 2 you are going to get as 8. So I can write 2V1 equals to 8. So V1 become 8 by 2. I can write it as 4 volts. Okay. The node voltage you are going to get by using the nodal analysis is V1 equals to 4 volts. Okay. So n number of nodes are there, you can solve by application of this KCL and you can solve those equations and you will get the node voltages. Okay. So one more point, I can go here, super node technique. Super node technique. So what is this actually? When ideal voltage source is connected between two non-reference nodes, it is possible to find solution by using super node technique. Okay, so let's take a simple problem. Here there is a current source, okay, and a resistor is there. Now I have a ideal voltage source, okay, it is connected between two non-reference nodes, and there is again I have a current source. Okay, this is 5 amps, this is 1 ohm. Let's take this is also 1 ohm. You can take this is 10 amps. this voltage you can take it as a 2 volts. Okay, so by general method or general procedure of nodal analysis, we are not able to find what are the node voltages. If the voltage source, ideal voltage source, is common between the two non-reference nodes, so let's, you can take this is node 1, this is node 2, and you can take this is a ground node or 0 reference node. That node you can take it as a 0 only, and you can assign the node voltages. You can take V1 and V2 here. Okay, so if this type of problem occurs, the general procedure whatever we discussed earlier, it is not applicable. So by using super node technique, so we need to apply nodal analysis or KCL at a time on both nodes at a time. Apply solution for this. Okay, apply KCL at node 1 and 2 at a time. Similar way, in case of mesh analysis, we discussed if a current branch is common between the two loops or meshes, we can apply the KVL in both loops at a time. The same concept I am applying here in case of super node technique. So V1, this is the highest potential point. Let's take I1, I2. You can take this is I3, and here also you can take I1 dash, I2 dash, I3 dash. So this one you can remove now. So you need not to consider this voltage source, the dotted one, and rest of the circuit you can apply the KCL both the nodes at a time. So I can write at node 1, I can write that is I1 plus I2. Next come to the node 2, that I2 dash, and you can take that is I3, which is equals to 0. So I1 I can directly write that is minus 10 amps. The direction of current source is already given, that is opposite direction. I can take minus 10. Plus I2 you can take that is V1 minus 0 by that branch resistor 1. Next I2 dash, that is current flowing from node V2 minus 0 by that branch resistor 1. Plus I3, you can take I3 is the direction of this one, and opposite direction having the current source, I can take that is minus 5. Take it as 0. So minus 10 plus V1 plus V2 minus 5 plus V2 minus 5 is equals to 0. So you can write V1 plus V2, which is equals to 15. You can take 1. Now you can apply the KVL at, that is a common source, by using the super node technique. By super node technique, so I can write that is, so that is connected like this. This is V1, this is 2 volts plus minus, you can take this is V2. So I can write V1 minus 2 minus V2, which is equals to 0. So V1 minus V2 equals to 2. You can take this equation number 2. Okay, so by solving equation 1 and 2, by solving equation 1 and 2, I can write the V1, I am getting it as 8.5 volts, and V2 I am going to get as 6.5 volts. Okay, so this is the concept of super node technique. Next video we will discuss the next topic. Thank you.